Hi, my name is Kangdong, and this is my project pitch for CS 898BA. My project is automated detection and classification of 3D printing failures using image processing and deep learning. 3D print job can run for hours and failure like spaghetti, stringing, and warping often go unnoticed until the print is already ruined, wasting both filament and time. If these failures can be detected early, a printer could pause or alert the user before more material is wasted. That leads to my research question. Can image processing combined with deep learning improve automatic detection of 3D printing failures? This project focuses on three common failures, like spaghetti, shrinking, and warping as the core classes to detect. The dataset I'll be using is 3D print color detection dataset from RoboFlow created by Kirby Fractal. It contains 4,549 labeled images split into training images, validation images, and test images across the same three file classes. You can see the examples images here. It shows a different visible failure mode which give the model a good variety of cases to learn from. To inform my design, I look at three core papers. YOLO 26 represent a more than one stage detector, optimized for fast detection. Faster RCNN is a two-stage detector that prioritizes accuracy over speed. And CLAHE, contrast limited adaptive histogram equalization, is an image enhancement technique used to improve image contrast before detection, which is directly relevant to image processing side of this project. The first design that I consider is YOLO. The pilot is straightforward. Input image processing, then YOLO produce a bounding box and class prediction in a single pass. The advantages are speed, real-time, capability, high MAP, and easy deployment, which matter if this is ever used for live print monitoring. The downside are that YOLO can struggle with small defects, have lower localization precision than two-stage detectors like RCNN, and is also sensitive to class imbalance, which is a real concern here since failure types won't appear equally often. The second design is fast RCNN architecture. Its highlight is more involved with input image processing, CNN backbound, or a region proposal network, OI pooling, and finally classification plus bounding box regression. Its advantages are high localization accuracy, strong performance on small or difficult object, precise bounding boxes. It is a widely used benchmark architecture. The trade-offs are a slower inference because of higher computational costs and a more complex architecture overall. Beyond just feeding raw images into a model, I'm proposing a structured image processing pipeline with three-state compare. A baseline is just RGB trade into a model. For method one, we convert RGB into LAB color state and then apply CLHE before the model to improve the contrast, even uneven lighting condition, which is really common in print bed images. And method two goes a step further by adding canny edge detection after CLASE to emphasize the changing red light edges that are characteristic of spaghetti and changing colors. I'll be evaluating whether each added step actually improve protection over the baseline. For my model selection, YOLO will be my primary model because its fast inference is essential for real-time 3D printing monitoring and is efficient for deployment. Faster RCNN will serve as my comparison model since its high localization accuracy and stronger performance on small defects, give me a useful benchmark against YOLO speed trade-off. To evaluate both models, I'll use MAP at 50 as the primary detection accuracy metric, MAP from 50 to 95 for a stricter evaluation, precision to reduce false positive, recall to catch missed color, and RU to assess bounding box accuracy. These are the core forces informing my design. The YOLO 26 architecture paper, the Arsenal Fast RCN paper, the CLAHE enhancement paper, and the RoboFlow dataset that I'll be using, which is licensed under CC BY 4.0. Thank you so much for hearing.